Okay, rational functions and their graphs. Okay, a rational function. Here we go. Quotient of two polynomials, looking something like this. Right, 1 over x, the most basic one of all. There's the graph. Here's 1 over x squared. Here's some more complicated ones. Okay, we'll be looking at how to graph these. Again, all these are rational functions. Okay, so if we take 1 over x minus 3, what's the domain of this? Now, we have done this before. Remember, the denominator cannot be 0. Okay? Right, in other words, for this one, can you see x cannot be 3? Okay? Just set it equal to 0 and solve. So if x cannot be 3, here's the domain. Negative infinity to 3, and then 3 to infinity. So remember, x cannot be 3. So remember that when you go to graph these. X cannot be 3 for this one. Here's the graph, and look. Okay? So this is what it looks like. But actually, now, I'm going to put some sort of imaginary line down here. Okay? Now remember, because the graph is not allowed to touch x equals 3. So when you look at these points here and here, it gets closer and closer to x equals 3, but doesn't actually touch it. Sounds weird, but anyway. Okay, so let's have a look. So we looked at the domain of 1 over x minus 3. How about some of these other ones? So can you see, for this one here, just x cannot be 0. There it is. Okay, here's interval notation. For this one, this is also x cannot be 0. There it is. Now, when you get more complicated ones, again, we're just looking at the denominator right here. Okay? Now for this one, we factor it, and again, do this. Remember, this is where it can't be. So x cannot be negative 2, and x cannot be positive 1. Here we go, right here. In other words, this is what it looks like in interval notation. Remember, x cannot be negative 2, and x cannot be 1. That's how I'd write it in interval. For this one, and this, let's just keep going. But again, look at this. We're just literally factoring the denominators. Okay? Factoring the denominators. Okay? So that's how you find out what the domain of these rationals are. Okay, here it is again, 1 over x minus 3. Now, as I drew that one earlier, remember this? Okay, because I'm saying if x cannot be 3, the graph cannot touch that x equals 3 line. Okay, but this is what we call a vertical asymptote. Okay, a vertical asymptote. There it is. Now, when we go to graph these rationals, this is what we might put on the actual graph paper itself, just the vertical asymptote. We're not sure what the graph will look like straight away, but at least we can put on the vertical asymptote, okay? And there it would be. So let's keep on going. Okay, so asymptotes, vertical asymptotes. Can you see, if we go back to this one, okay? As x approaches this 3 line, y is going up to infinity, or f of x is going to infinity, okay? As x approaches the 3 line here on the negative side of it, the y, or f of x, is going down to negative infinity. So let's have a quick look at just summary of all that. Okay, here we go. As x approaches 3, or rather a this time, it's just a letter, okay? Imagine if it was 3, okay? On the negative side, so we'll tend to write it to negative there, okay? Y, or f of x, is going up to infinity. And that's what this says down here. Again, as this one, as x goes to this a, imagine it's 3, but again, on the negative side, it's on the negative side of this asymptote. Y, or f of x, is going down to negative infinity. And that's what that says there. So, as x approaches this a on the positive side, okay, this is the a plus, on the positive side of this over here, again, y is going up to infinity. As x approaches this line on the positive side here, okay, y is going down to negative infinity. And again, that's what all this is saying. Okay? So, determine a vertical asymptote. Okay? Basically, what we're doing is we're putting the denominator equal to 0. Okay? Right, let's look at some more things. Okay, let's have a look at some of these. Okay, if we're trying to find the vertical asymptotes, then here we go. We just need to factor this. X squared plus 2x minus 8 will factor into x plus 4x minus 2. So again, we can't have negative 4, we can't have positive 2. So again, those are the two vertical asymptotes. You see that? One at negative 4, one at positive 2. By the way, again, just to look ahead, watch this. If I do this, ready? I'm going to ruin everything. There, I've just set x equal to 0. Okay, isn't that the y-intercept? So what's the y-intercept? Positive 11/8. Two negatives, 11. Isn't that about 11/8? Can you see that right there? That's 11/8. So remember that. Okay, edit. There we go. Right, let's look at another one. Okay, so we've got this one here. We factor this. Okay, again, looking at the denominator. Just looking at the denominator. Take an x out. Difference of squares. So here we go. Here is the denominator all factored. In other words, here, x cannot be 0. X cannot be -1. X cannot be +1. So, what I would normally think of is I've got vertical asymptotes at 0, -1 and +1. But look, the x is here. Cancel. Now it could have been an x plus 1 on top that cancels the x plus 1 here. That could have cancelled. Here it was just the x. So actually I've only got vertical asymptotes at -1 and +1. And look over here. Here they are. Get my little arrow up. The -1 asymptote and the +1 asymptote. So because I cancel these x's, but remember x cannot be 0 still because it was there on the denominator. So x cannot be 0. So what we have here is, look, we have a hole in the graph at x equals 0. Okay, and that's where that hole's there. So remember that for future kind of graphing. Okay, so again, me just factoring the denominators to find out what x couldn't be. Okay, so x can't be 0, x can't be -1, x can't be +1. But I also factored the numerator here because look what happened, just to check. And this cancelled the x, so it actually cancelled one of the vertical asymptotes that I thought I might have. Okay, but it is still there, so x cannot be 0, so for this one it's just a hole in the graph. Okay.